We don't care about this anymore. In fact, we don't care about any of this anymore. All we need is the whiteboard and some questions. Yeah.
Can you go to number 11?
Number 11 on the home. Remind me which one that was.
That is prove the language in L each W on the number of A's in W is equal to the number of B's in W times the number of C's.
Yeah.
Sometimes.
That number of A's in W equals B's in W. All right. If we're solving this, I think some people have seen me go over this, but it's always worth the review. Just a second. Excuse me. I didn't decide. A cat decided that a great place to sleep last night was right up against my face, and I'm horribly allergic to my cats. This morning is going to be interesting. All right, so an intelligent string for this, it has to adhere to the language. So we're going to pick a W that was A to the M squared, B to the M, C to the M, because M times M is M squared. So any context-free grammar that works for this language in general must also work for this string. And since it is longer than M, there must be a sequence of productions that produces at least one recursive step going from one non-terminal back to itself. From here, we want to break this down into UVXYZ, B to the I, X, Y to the I, Z, where this is just UVXYZ to begin with, but it should also pump to stay the same. So we're going to have some cases. This is where we care about what VXY is. So one would be all A's. Another would be it's all B's. Another would be it's all C's. And since it can scale anywhere in the string, sliding window of length M, there are also cases for some A's and some B's. And a last case for some B's and some C's. Cases 1 through 3 are pretty trivial. If VXY is all A's, that means we can either pump up or pump down, and the number of A's are going to be more or less than the square of the number of B's and C's. If it's all B's, pump up or down, and now B times C is no longer M squared. You can show that relatively easily. Same thing for C. You can basically bundle B and C together. It's exactly the same idea of when you have B times C, it's commutative multiplicatively. So due to the commutative rule of multiplication, it doesn't matter which you increase or decrease between B and C. If the product of one isn't M squared, then the product of the other will also not be M squared. B's and C's is an easy case because when we break this down, if the length of V is empty or the length of Y is empty, and one represented B's, one represented C's, it breaks down into one of these three cases. So we only have to distinguish and worry about a case where there's at least one B and at least one C. If that's the case, then you're at least having M plus 1 times M plus 1, which is, of course, going to be greater than M squared, and any other value that you could pick for that is going to also be larger than M squared. The only tough case is the breakdown between A's and B's. And the easiest way that I've found to break this is to break this down such that, so we're going to start with some amount of A to the M squared, B to the M, and we're going to add to that. So we're going to break the length of Vy down into two components. I've been using K and L for this. So it's K plus L. And length of Vy, as we know, is less than or equal to 1 and less than or equal to M as the legal bounds of what Vy is. So K represents the amount of Vy that's going to be added to the A's, and L represents the amount of the length of by that's going to be added to b's. As we do this, we can see that the new string uv squared x y squared z is going to now be basically a to the m squared plus k, b to the m plus l, c to the m. And we need to be able to show that for any possible value of k plus l, there exists an I that does this. But what we'll see is if we just instantiate L with the worst case, there's no way to create a legal K that creates the next string up in this language. So let's say in the worst case, L equals 1. There's no way for there to be fewer B's that we're adding than if we break this apart into one of the length of by goes to B and the rest goes to A. So if we do this, what we see is if we multiply the number of B's times the number of C's, we get m plus 1 times m. Which is m squared plus m. And if we further break this down, what we see is this is how much we have to add over here in the A's in order to get to the next perfect square. So that tells us what we should back substitute when we set L equal to 1 is that K must be greater than or equal to M, which means that K plus L is greater than or equal to M plus 1, which we can tie back to this rule and say that is not possible. There is no way to create the next legal bump up in B and keep K plus L less than or equal to M. The smallest possible value this can be is M plus 1. Because that's how many further A's are needed to get to M plus 1 times M. So we need to add M here and 1 here. And L can only be larger than 1. And if L is larger than 1, then any M plus 2 times M or M plus 3 times M is just going to be greater than, you're going to need to add more than M to that. So this is the floor of the number of characters that we would need to add, and it's already out of bounds of the number of characters that we could add to that. So that's the intuitive route that I take. Obviously, you need to write out the argument and write out the math for that. But to me, the hardest part of this is coming up with the intuition. Once you have the intuition, you can just write out the logic, the steps of how that is shown. You just break down this into K plus L, show that, derive the this, then this, then this, then this. Here's the contradiction. Tie it back in that if we're in A's and B's, we actually can't have a legal breakdown of M characters that creates the next perfect square. Questions on that idea? What else can I answer?
I have a question. I'll just say the question. Find a simple grammar for L equals A to the N, B to 2N, and is greater than or equal to 10. And you're trying to find a simple grammar.
Yeah. Was
A to the N, and then B to the 2N.
yeah. So in order to do this, basically this breaks it down into whether lambdas are allowed in simple grammars or not. And the intuitive way to discover that they are allowed in simple grammars is that simple grammars map to deterministic pushdown automata, and lambdas are allowed in DPDAs as long as there's a different stack character on each one of the lambdas. So we just have to make sure that each simple grammar rule, when we do include a lambda from that non-terminal, isn't creating some ambiguity with one of those symbols.
And,
So
sorry, N is greater than or equal to 2, I guess.
yeah. So if we do this, we find that no matter what, an A is going to start us off. In fact, we know that at least two A's are going to start us off. So in order to do this, we need an S production that reads that A and then goes into something else. We need another production that reads another A, goes into something else. And now we need some way to map future A's with something that is two B's. So I'm going to have something represent two B's. So we'll leave space for the B, but C is going to represent the idea of two B's. So far, we're in simple grammar form, no non-terminal leading to really more than any one possible rule. So this allows there to be exactly two B's here at the end. Now we need some ability to add additional A's paired with B's. So I will draw this out where we have an additional A followed by exactly two B's with the ability to recurse on yourself. But now is the point where we need that lambda. We need some way to terminate this grammar. So this forces there to be two A's, the associated B's. This gets you to there for the first one, this gets you to there for the second one. I guess we want a single B here, definitely it should be B and D. When we add an A, now we need to add two. This adds a single A with that. This adds a single A with now, oh, this is 2B. The single A does get C's, my bad. Then we should be okay. We just need a single lambda there to terminate that. And this doesn't create ambiguity with regard to the rules because we're looking at nothing or an A. And that can be determined whether there is something else to read or not in line.
So is the D production not needed?
The D production, this is what forces there to be two B's in this case. This should not be B, this should be D. Okay, that's why. The D production would be needed if there was no other way to reference it. But yeah, this should be D, sorry. Does this logic make sense? I'm just coming up with this on the fly, so there may be an issue with it. You can do something like try to break the lambda out of this. If you try to do that, you very quickly find that, all right, I need the right-hand sides of B's to be able to be empty. If you do this, then you're adding an or AC to this rule to do that. And obviously this rule is not allowed in a simple grammar. So we can't move the lambda up from this and have the grammar stay simple.
What if? I haven't had enough time to process this.
Yeah.
One of my issues that I'm trying to understand, if S goes to A, C, and then, so what if we just keep looping on C and just keep adding B's? Isn't
You
that?
can't. This goes straight to D, which only allows for there to be one further B.
Oh,
So the idea is wherever there's a C, it's going to lead to exactly two B's.
I thought I misread it. I see now.
The rules for context free.
Yeah. There are almost none of them. Very nice. All right, for a context-free grammar, we're going to have there's a series of production rules where we have a I think that might be the easiest way to see it. We need at least one non-terminal or terminal on the right-hand side of a production. We can't have a non-terminal going to nothing. We have exactly one non-terminal going to really one or more non-terminals or terminals, and we can intermix those in any order that we want. There is no restriction on the number of them, the placement of them with respect to each other, etc. Every other grammar type that we've seen has had some restriction here. And the only restriction to a context-free grammar is actually right there, the single non-terminal on the left-hand side. So almost full power. At least full power on the right-hand side of a production. Is there anything follow-up with regards to that?
I guess I'll just ask you, so how do context-free grammars model programming language syntax, and how do they fail to model syntax? I know we
Yeah.
have this in class, but just as we're.
Yeah, so we found that we could find context-free grammars that both mapped to the idea of mathematical parentheses to scope, and we just have some way of mapping either the open curly brace or an open parentheses to something like an A and a closed parentheses or a closed bracket to a B, something like this, and then you can write a context-free grammar that allows us to model scope. We either had the ability to open and close and nest scopes without the ability to have scopes sequentially, but we also found there was a context-free grammar that allowed for sequential scope in addition to nested scope. So that's how you would want to answer a question like that of how does this model programming syntax? Well, we replace the scope entry and exit characters with the equivalent of an open and a close in a grammar. And now we can model any mathematical open and close concepts and scope open and close concepts. So that helps us to do things like, because we're using an NPDA models with a stack, it allows us to represent something like the call stack. So when methods are called by methods, that allows us to recursively call a method and place a marker. It's exactly the same thing to be modeled in with an NPDA and a stack, where the non-terminals would be the method names. And then the terminals would be anything that is produced by that method call.
What about how it fails to model semantics? What does that mean exactly?
So semantics in this case is the meaning. So if we're looking at something that is syntactically correct but semantically meaningless, does anyone have a fun or interesting example of that in a programming language? Something that's syntactically correct but semantically garbage.
int A equals 3.2.
Sure. This is a Java statement,
I was thinking C++.
C++ statement, a C statement, any C language style is going to work here. But yeah, here's a statement that, is this something that we could do? The compiler at the syntax step would not have an issue with this. We have a variable, we have a legal variable name, we have an assignment operator, and then we have an expression. That looks legal to me, but it's at the semantic step that we come up with an issue that we can't actually put this value in this variable type. But that's not a syntax issue. Legal variable type, legal variable name, equals operator, expression. That would be in your grammar. That's something that we can do. But that's not the only, the syntax step is not the only step of the compiler, but it's the step that we are discussing with regards to a lot of the grammars that we've talked about so far. Any other follow-up questions to context-free grammars while we have them here? All right, Ty, do you have another question to go into?
Yeah, can you do, constructing an NPDA, the language, L equals W, where the number of A's and W plus the number of B's and W is equal to the number of C's and W?
Yeah. All right, first thing to notice about this is that order doesn't matter. This string can start with any of an A, a B, or a C. And we just care about mapping the equality here of the sum of these to the total of these. But since order doesn't matter from that very first state, we can start to see any of these characters. So I'm going to start with a state where we assume the bottom of the stack character is on the stack already. From here, we can self-loop on, we need to read an A, read a B, or read a C. I'm going to decide before I even begin what my stack characters are going to represent. And to be able to determine this equality, what we really care about at each stage of reading a string is how many of each of these characters do we have more than the other or less than the other. So I'm going to state that a 0 means that we've seen more A's plus B's than we have C's. And the number of zeros that are on the stack are the number of more A's and B's than we have seen C's. And if we have 1s on the stack, that means that we've seen more C's than we have A's and B's, and the number of 1s on the stack would be the number more C's that we've seen than A's and B's. So we don't care about the total number that we have seen, we just care about the relative number that we have seen to each other. When we start with a string, we have seen 0 and 0, so it makes sense that the stack is empty. We haven't seen any more of one than we have of the other. So that's what the bottom of stack symbol on top of the stack means, is that we've seen an equal number of the left-hand side and the right-hand side. All right, so we need a self-edge. Because it doesn't change the state that we are in, we can always see A's, B's, or C's. If we see an A or a B, so let's start with, we see an A with a Z on the stack. We need to be able to handle a B with a Z on the stack, a C with a Z on the stack, an A with a 0 on the stack, a B with a 0 on the stack, a C with a 0 on a stack, an A with a 1 on the stack, a B with a 1 on the stack, and a C with a 1 on the stack. This grows in complexity relatively quickly. But we just need every possible bottom of the stack character. We kind of need every single pair at this stage, because at any point, any character is legal to appear in the string. If this were ordered differently, like the A's have to come before the B's, and the B's have to come before the C's, we need different states to read the A's, the B's, and the C's, because we'd be transitioning between being able to read A's and being able to read B's. But again, since these come in any order, or can come in any order, we combine them in a single state, because we need to be able to handle that. So if there's a Z on the stack, and we see either an A or a B, we put the Z back on the stack, but now we've seen one more A or B than we have C. In this case, whether it's an A or a B is not important. It's the same idea, it's added to the left-hand side of this equation. We've seen one more of the left-hand side than we have of the right-hand side. We see a C, then we want to have seen one more C than we had before, and throw the bottom of the stack character back on. If there's a 0 on the stack, that means we've seen more A's or B's than we have C's so far, so that means add an extra one. If we've seen one more A or B than C, and we see another A or B, we've now seen 2 more. Regardless of what that is, we're adding one more of that, so we should add an extra 0 to the stack. Increasing the height of the stack by 1. If we see a C and there's a 0 on the stack, that just means that we've seen more of this. When we see one of these, we've seen one fewer of this than we have. So we should take it off. This would say if there were 2 zeros on the stack and we saw a C, that means we've seen 2 more of these than we had of this, and now we've seen 1 fewer of that. We've seen 1 more of this than we have of that. So that means take a 0 off the stack. If there's a 1 on the stack, we see an A or a B, we want to get rid of it. We've seen 1 fewer C than we have A's and B's, but we've still seen more C's than A's and B's because there are still 1s on the stack. It's the exact opposite. For a 1, we want to add an extra 1. If we've seen more C's than A's and B's, we see another C, we've seen yet another C, more C's than we have A's and B's. We can only accept this string when we're at equivalence here. So to get out of Q0, we need to have an empty stack. We cannot be in a state where there are more zeros or more ones, or zeros or ones on the stack, because it tells us we've had more of this than that. So without reading a character from the input, because that doesn't require a character to read to check that the stack is empty, we're just going to make sure that the stack was empty, throw it back on, get to a final Q1 where we would accept. And again, we accept here for the 3 criteria of an NPDA. That's making sure that we're at the end of the string, that we have the bottom of stack character, so the stack is empty, and we're in that final state. So the 3 things that we need to accept an NPDA. So this is one of those cases where the entire difficulty of the problem is in the sheer number of transitions in that initial state. Yeah.
Describe, here's a list of structure.
Yeah, so this would be something like, if I had you do this, then we would say there's a transition here from, that was like a musical note, not a delta. Oh well, we're gonna go with musical notes in here. If anyone wants to sing, please don't. I just assume none of us have any singing talent. That's probably not true, but. So the exit criteria for this is that on a Q0, if we're in Q0 and we read an A with a 0 on top of a Z with a Z on top of the stack, then we need to transition to the state Q0, and basically we're going to now push the 0Z. So here is the push or the pop. So it becomes very similar in style to these straight transitions that you see here. It just becomes here's the information you need on the way out, here's the information you need on the way in. And then you would just write that for each of these sequence of transitions, and that can help depending on whether you want to see this visually or whether you want to write this out as a series of transitions. If this becomes a larger scale, sometimes it can be easier to break it down into something like you would have the Z on the stack set, the 0 on the stack set, and the 1 on the stack set. Or you could even break this down into the reading of an A, the reading of a B, and the reading of a C. And then you can have a series of transitions for that, and that would help you break this down. And this is kind of a 2-dimensional problem, and that for each possible stack symbol, for each possible input character, if you're not thinking in that regard, but it makes more sense to write labels and then transitions that meet those labeled criteria. It's an easier way of breaking down what is a 2-dimensional problem into something that is easily, you can come up with everything and make sure that it's complete. But again, on an exam, I'm probably not going to say, write this as a series of transitions, but you need to be able to read a series of transitions like this. If I said, an NPDA modeled by this, do something with it, or run through an example with it. So you should be able to read this more so than memorize how to write this. If I'm having you construct an NPDA, I'm probably not telling you to construct it in one way or the other. I don't like placing unnecessary limitations on you.
Sorry, can you repeat really quickly how the exact order of what those symbols represent?
Yeah, so we have kind of the outgoing state. I'm going to call it the from state. And then we just need the tuple here of this is kind of the input, the character in the top of stack symbol. So this is the This is the, did I say 0 here? This is a pop and this should be an A. That's why this makes no sense. All right, now they're labeled a little bit better. Follow-ups on that or any other question?
That's your did profile, so that's the question.
Yeah,
Yeah.
questions are always good. I occasionally make mistakes. As much as being a machine would probably improve me, I am not one. Although that I'd speak in much more monotone or maybe Siri-like. I don't know. If I were to speak in monotone, how would I speak? That's a great question.
You also make a grammar for that same one.
Grammar for this language. Yeah. So if we're doing this, we just need to make sure that however it is that we're coming up with A's and B's, we're also coming up with C's. So whenever we make a C, there is a pairing of an A and a B somewhere. Whenever we make an A or a B, it has to come in a pair of A's and B's with an associated C. So if we're doing that, we're either seeing an A and a B with a C, or a C with an A and a B. So I just really need to come up with all of the possible combinations for which that could happen. So if I see the terminal C, then follow it up with an A and a B in some respect. So we could make some non-terminal that represents the need for an A and a B. And this can now be an AB or a BA. And we need every possible order of this could come before the C or after the C in any order. But it could also, the C could come in the middle of this. So we need the ability to split up into a single A and a single B. So we'd have a C followed by a single A and a single C. So this is an A, this is a B, or we could have them in that order. That is everything with a C, making an A or a B. But now we need the ability to end with that or recurse to an S on that, same idea. So we could then just add an SS as the ability to recurse and do this multiple times. So this now terminates by getting this is the last C, and it says there are multiple C's. So now this grammar is kind of in a form of identify where the C's are and then throw the A's and the B's in some way, shape, or form. Question?
Wouldn't this not work because A plus B is equal to C, and if you add 2 to 1,
Yeah, it is A plus B equals C, isn't it? Yeah, so we have, yeah, there should be multiple C's for each A or B. I have this completely mixed up. That is a great idea. So this needs to be an A or a B. That makes it easier. Significantly easier. This would be a harder problem. If this is a C mixed with an A or a B, then an A or the B is coming before or after. So we just have to then say that A is either A or B. We don't need this. And for each C, the A or the B comes before it or after it. And we can break this down. Now we still need the SS, the ability to construct something of multiple C's. So you would do SS for each C in the grammar, and then start to do that. Could we handle all of the C's being at one end or the other end if we did that? So something like CCAB.
No.
We go S to SS. From SS, we have to have each one of these has a C in some capacity. Where is each one of those? The first one would want the C to be either at the beginning or the end. There's no way to force it to be at the end of both an A and a B. How do we handle that? We have to distribute this S somewhere into this, allowing for extra options. It's not necessarily that this idea is happening sequentially, it's that it can happen recursively. So to make it recursive, we just have to add options for where the S is in this. Either we have an SCA or a CSA or a CAS. And then do the same thing for the AC. The S can go anywhere. We have S, A, C, or A, S, C, or A, C, S. That becomes a little bit grosser. But now at least it's recursive. We can recurse the S wherever we need inside of that. So now when we see the CCAB, what we should be looking at is the outside characters. When we see a C, it's mapped to something else. If it's mapped to another C on the outside, then we need to recurse on the inside and create an A and a B for each of that. So that would be a C and an S, because the S can produce the C on the inside, but then the structure of that would force the A or the B to be somewhere inside of that as well. So the C and the B tells us that we need a C first and an A at the end. So this S would go to CSA. Since there is something on the inside of this, we need to make sure that we recurse in the middle. This A then becomes the B. We'll kind of do this rightmost, so we get CSB as an option. Then this S becomes a C and an A, but since there's nothing inside of it, we should choose the one of these that does not have an S associated with it. The C comes first in this case, so they should be S is replaced by CA, where this A becomes an A. I think this works. I kind of went off the board here for those of you who were remote. Oops. It's everything.
This requires that the length of the string be at least one.
It does. Yeah, so you can have S go to lambda as well, and then you actually don't need the.
Well, if you were
Other
gonna do that,
case.
wouldn't you have to put that down so that you don't get an uneven one? Because if you just add four lambda to the end of the S.
Yeah, it's not forcing. I don't think so. Everywhere we have a C, we have an A. So that forces there to be an A or a B. I think we'd be okay. But yeah, if we add a lambda here, then we allow for the n equals 0 case. But then we also don't need the n equals 1 cases over here. You can just have them go to lambda at the last time. You make space for something, and then that space for something goes to lambda, rather than having to do that at the end. Just send it to where it usually is. There it is. Questions on that? What else can I go over? So this is a very raw process of mine. This is the process that I would use on an exam because I'm being shown something that I haven't thought about in a long time or possibly ever, and just throwing together a solution. So it's a very raw process of how am I analyzing the structure of this language? How am I trying to fit that structure into a grammar's form? You can try something, realize there's an issue with something like the SS because it forces it to be sequential. And there's nothing that forces sequentiality in this language. So that's a bad attempt. That's not going to produce something that we want. We need something that is recursive so that we can analyze the string from the outsides in. As we do that, what are all possible forms of the outside in? Where could the C's be? They're paired with some A or B. Construct from there. Yeah, this is not a practiced process. It's not, I looked at an answer, here's how I understand the answer, here's how I'm displaying the answer. It is, here's how I'm generating the solution, which mimics exactly what you're doing on the exam. So whatever you can do to have a higher level understanding of how to put together something like this, that will help you a lot when you're looking at something that you haven't seen before. Just the ability to abstract and say, how can I fit rules of grammar to rules of language? What else can I help with? We still have time. One more, yeah.
If no one else has, then you just do a sequence of instantaneous descriptions for that same language.
Yeah. So we need a string in order to do instantaneous descriptions because the string is it's the going through the grammar or going through the NPDA to do that. So what string do we want to use?
And that should be in the language, not the language, right? This is just trying to parse if it's
Yeah. It's better if it is because you can show the process, but eventually if you're doing instantaneous descriptions, you run into a dead end. But the instantaneous description will show the path. If you're searching for that path and there is non-determinism in the grammar, then you're going to kind of fork your instantaneous description, and we could go this way or this way. So generally instantaneous descriptions are used to show here is the path through the grammar that shows that it is possible. So that's the most likely question that I would give you on something like that is prove that this string is in this language by showing a sequence of instantaneous descriptions.
I guess you just use ACBC as an example.
Yeah.
So on the exam, for the instantaneous descriptions, they won't be non-deterministic.
So it could be non-deterministic, but your answer will be the path that shows that it is, not the 10 paths that lead to dead ends, but the one path that leads to success.
Okay.
Yeah, so we said ACBC. So close to a band name. All right. What is an instantaneous description? So we've seen two of them now in class, but only one of them would be able to show up on an exam. What is the context-free grammar instantaneous description form? Who has that ready to go?
UWU.
Yep. So we had QWU representing what? What's the Q, what's the W, what's the U?
U is the start state.
So we have the from state followed by
Current string.
current string. The remaining part of the string followed by,
What's the stack?
yeah, the stack contents. Much better to think of this as an idea rather than some letters. If you have this on your note sheet and just this, that won't necessarily help you. Yeah.
A little bit confused about so I thought W in this case would be the part of the string that's been parsed so far.
Was it so far? I think it was left to go so that we could see what we still had to. By the time that's empty, we know that we're done. Or am I completely misremembering that? That is possible.
I think in those slide notes, it is like it goes down. Like you have
Yeah.
string that with each.
Yeah, it's the part of the string that hasn't been parsed. So we're going from, we have the entire string left to read all the way down to there's nothing left to read. So we know that we've produced it.
Yeah, so you read an input from W and then you remove it.
Yeah, so where we start at the very beginning of this, it's a snapshot. And at the very beginning of this, we have nothing read. So the from state, we're about to transition out of Q0. So we would have a Q0 The remaining string is A, C, B, C, and the stack contents is just the bottom of the stack character. So that is where we begin. We very long turnstile. From this, we're going to make a transition from Q0 back to Q0. So we know we're going to be back in Q0. We're going to have read the A. So what's left to read is the CBC. And what's on the stack now is when we read that A, we pushed a 0 onto the stack on top of that Z. So we'd have 0Z as our stack contents. To read the C, we're going to pop the 0 off the stack, stay in Q0. So Q0, we've now read the C, so what remains is BC. The 0 has been popped off the stack, and all that's left on the stack is the Z. We would turnstile, we stay in Q0, we read the B. That pushes another 0 back on the stack, so all that's left to read is a C. We have the 0 back on the stack. We're still in Q0. We read the last C, that pops the 0 off the stack. So we have nothing left to read in the string. We have an empty stack. That tells us we can transition to the final state. We don't have to read a character in order to do that. So the fact that there's nothing left here doesn't prevent us from making that transition. So the last place we're going to be is in Q1, nothing left to read, and the stack is empty. Since we ended up in a final state, we're at the end of the string, Q1. There's a comma after the Q1, not double comma. We're good. And the stack is empty. The 3 conditions that we need for acceptance in NPDA, they're apparent in this QW and U. We have final state, empty or end of string, empty stack. 3 things we need to accept, so we can accept at that point. Yeah.
Just to clarify, not with this problem, but there are problems where you can have the accept off of the non-empty stack or.
Only if you have, so you have to have an empty stack, but you might have in your final state here a self edge that does something like remove things from the stack. So if this were not equal to, we expected there to be more C's than A's and B's, then we wouldn't want to transition on a Z, we would want to transition on a 1 that we pop for sure. This would force there to be 1 more C than there was A's and B's to get to the final state. But if there were 2 more C's than A's or B's, there'd still be something on the stack at this point, which we technically can't accept. So we need to duplicate this rule to empty the stack so that we end up in that position. So there would be 1 more transition here. Don't read a character, pop a 1 off the stack. And this would say, regardless of how many 1s there are on the stack, we can go through a process of removing them from the stack so that we can reach a point that we are at the end of the string with an empty stack in a final state. We're out of time already. How wild is that? All right. Well, I have office hours starting now. So if I didn't get to a question that you have, feel free to swing by. If you'd like some help with any other concepts, if you'd like help getting started on your project, if you'd like help getting started on the next homework assignment, if you'd like to complain about how much work we have in this class, I'm open to all of that. Come trauma dump on me. That's what I'm here for. I will eat your stress and take it home.